let's talk about a mathematical puzzle that has stumped the greatest minds for centuries. I'm talking about high-degree polynomials, these equations that can look, well, frankly, terrifying. But what if a fundamental belief we had about them, that you can't really solve them exactly, is just wrong? Just look at this thing. This is the challenge we're going to tackle in this explainer, an 18th degree polynomial. Seriously, for generations, the absolute best anyone could hope for with an equation this gnarly was to get, close to the answer using an approximation. But today, we're going to find the exact solution. So what's the big deal? Why is this so hard? I mean, you've got formulas for second-degree quadratics, right? Even for third and fourth-degree equations. But back in the 19th century, it was proven that there's no general one-size-fits-all formula for anything fifth degree or higher. Mathematicians basically hit a wall, which is why they've had to get creative. So this leaves us with two totally different ways to think about this. You've got the classical path, which uses these fancy numerical methods to kind of inch closer and closer to an answer, but it's always just an approximation, right? It's always got these little rounding errors. Then there's this new path, Ezouidi's Theorem, and it promises something much, much bigger, an exact symbolic solution. We're not talking about getting close, we're talking about hitting the bullseye. And that brings us to the hero of our story, a totally revolutionary theorem that gives us a brand new set of tools for this ancient problem. Let's take a look at what makes it such a game changer. Wow, I mean, that is an incredibly bold statement. This isn't just saying, hey, I made the old way a little better. This is a direct challenge to a cornerstone of algebra called Abel's impossibility theorem. That's the one that said you can't have a universal formula for these things. This new method is basically saying, actually, we found a systematic way to do it. So what is this thing, Ezouidi's theorem? Well, at its heart, it's a systematic recursive process. And that word, recursive, is everything. Think of it like a set of Russian nesting dolls. The only way to get to the very last doll is to open the one before. The theorem does the same thing. It uses the result from one step to figure out the very next step, and it just keeps going, systematically breaking the problem down until the answer just appears. Okay, now this formula is the engine that makes the whole thing go. Don't worry, we're not going to sit here and calculate it all out, but let's just see how it works conceptually. This formula's job is to create a new set of numbers, these S coefficients. And see that little S sub r minus 1 on the right side? That's the secret sauce. That's the recursive part. It literally uses the S value just calculated to find the next one, creating this perfect chain reaction that just dismantles the original equation. So here's how all those pieces fit together. The formula grabs some bits from the original polynomial, mixes them with some other standard math terms, and then, this is the magic, it feeds its own answer right back into the machine to start the next cycle. It's this beautiful, self-contained system for just demolishing complexity. Okay, the theory is cool, but let's see this thing in action. We're about to unleash this theorem on that monster 18th degree equation from the beginning, and, well, watch it get tamed. So here's the game plan. The first step is to use that formula to calculate a new set of 18 coefficients, which we'll call S0 through S17. You can think of these S values as the secret code, the hidden DNA that's going to reveal the polynomial's true, much simpler structure. So the process starts, and right out of the gate, something amazing happens. The formula tells us that the first 8 coefficients, from S0 all the way up to S7, are just 0. Poof! A massive chunk of the problem's complexity just vanished in the very first steps. And then we get to S8, and we finally get our first non-zero value. It's a huge, very specific number, and it turns out to be one of the critical clues to the whole puzzle. And then, just as quickly, the pattern of simplification continues. The very next 8 coefficients, from S9 all the way to S16, they're all 0 too. You can see what's happening, right? The theorem is basically filtering out all the noise and pinpointing the only parts of the equation that actually matter. Finally, we get to the very last coefficient, S17, and boom, we get our second and final important number. And with that, we have all the pieces we need. So let's just stop and look at what just happened. We started with this terrifying equation that had 18 different complicated parts. After running it through the theorem, we found out that 16 of them were basically just fluff. Only 2 of these new coefficients actually define the core of the equation. This is what the method does. It cuts straight through the chaos to find the elegant structure underneath. And now for the big payoff. We took this ridiculously complex problem, we broke it down, and we found the only 2 numbers that truly define it. So it's time to see what the final beautiful answer actually looks like. Remember where we started? This absolute jungle of terms and numbers? Just
تحت
burn that
الشوط
image in your
الزمالك
mind for a
سلامات
second.
الزمالك
Because
كتير.
after all of that, it simplifies to
عماد
this.
ثم
The
لعبة
entire 18-term monster boils
أصحابه
down to a clean, simple 3-term equation.
جاي
This was the true identity of the polynomial, hiding in plain sight the entire time. I mean, that is a stunning transformation from chaos to clarity. And from that simplified form, we get the exact symbolic solution. This is the answer. And yeah, I know it doesn't look like a simple number like 5, but that is precisely the point. This isn't a close enough decimal you get from a calculator. It's a perfect, precise formula that can generate every single one of the 18 exact roots. It is the key that fits the lock perfectly. And that really is the core breakthrough here. It's the power of moving from approximation to absolute exactness. Think about fields like cryptography, where security relies on the precise relationship between giant numbers, or physics, where you need perfect predictions for orbits. In those worlds, close enough can be a disaster. This offers a path to complete certainty, which really leaves us with a fascinating final thought. For so long, problems like this were just put in a box labeled unsolvable by formula. But if we now have a tool that can crack them open, it just makes you wonder, what other mathematical doors have just been unlocked? What else is out there that we've assumed is impossible? Today, we're wrestling with something, well, something that's historically been real in mathematical terms.
Yeah, we're talking about finding a solution to a very difficult problem.
Exactly. Forget your original quadratics. Think degree 18, a level of complexity where the usual formulas, well, they break down.
Something with a degree of complexity that
Welcome back to Easy Shot. Today we're wrestling with something, well, something that's historically been real in mathematical terms.
Yeah, we're talking about finding a solution to polynomials, but not just any polynomials. We mean the really high ones.
Exactly. Forget your high school
Have
programming
you ever
skills.
looked at a math
We're talking
problem?
human beings. A level of complexity where the usual formulas, well, they break down.
Completely. I mean, essentially, it's basic mathematics, right? The standard approach of making numerical equations mathematically easy.
Which gets you close, right? So you can above it. But
But in pure mathematics, it really feels a bit like devil's. You want the exact symbolic answer.
right. And that's our mission today. We're diving into a concept of this Ezouidi theorem, which makes pretty bold claims that you can bypass
Ah, so you can't guarantee the exact value. The process itself involves trimming things down, rounding.
Precisely. You're always dealing with numbers, inherently.
So we're perpetually stuck in the closed loop, which, yeah, it's frustrating if you're after mathematical theory. And this bumps up against the major variables.
It can. For anyone familiar with algebra, is that for classical sense,
Okay.
it uses schematic algebraic mathematics to structurally simplifying the polynomial itself through a recursive cycle, justifying a radical formula. It fundamentally changes the form of the equation using a polynomial.
So it collapses the structure.
Exactly. It collapses it into a structure and then solves it. It defines it as a right polynomial, a complex exponential or statistical function derived from a process, but not necessarily a simple radical, like finding the median of half the rounded outcomes. It excludes the classical method by using a new type of structurally rigid system.
So it sounds like Ezouidi is avoiding guessing with approximate numbers for mononomials. If everything's really symbolic.
That's precisely the idea. The theorem uses what's called a systematic method, a very structured step-by-step process, less like brute force than law of probability, carefully picking it apart into its own linear logic.
So it's not just a mathematical theorem, it's a mathematics algebra.
looked at a math problem and just thought, nope, no way, that's impossible. Well, for centuries, that's exactly what the smartest mathematicians in the world thought about solving certain high-degree polynomials. Today, we're going to see what happens when a new way of thinking takes on a problem that was basically considered impossible for generations. So, here it is. This is the beast, an 18th degree polynomial. Just look at it. For the longest time, the goal of finding the exact values for x using a single precise formula, well, it wasn't just hard, it was considered fundamentally impossible. You know, the standard playbook was to just give up on finding the perfect answer. You'd settle for a really, really close guess. But what if close enough isn't good enough? What if there's actually a way to cut right through all that complexity and find the perfect solution? What if unsolvable was never really unsolvable to begin with? To really get why this is such a huge deal, we gotta take a quick look at why the old ways just couldn't handle a problem like this. They literally killed it all. There's a fundamental reason classical algebra just stops working here. Think of it like this. You have two paths. The classical path is all about approximation. You make a smart guess, then you refine it again, getting closer each time. It's a powerful tool, but it's never perfect. Tiny rounding errors always sneak in. But this new approach, it promises something totally different. An exact symbolic answer, found through a structured process. No guessing and zero errors. And this quote gets right to the heart of it. There's a famous mathematical rule, Abel's impossibility theorem, that basically said you can't create a general formula for the roots of these big polynomials using stuff like square roots or cube roots. It put up a giant stop sign. But this new method from Mourad Sultan Ezouidi basically says, hold on, what if there's a way to drive right around that sign? So how does it work? What's the secret? Well, this new path is paved by something called Ezoudi's theorem. This is the key that's going to unlock this whole problem for us. So, what is Ezoudi's theorem? Simply put, it's a recipe. A very clever, structured, step-by-step process. The magic word here is recursive, which just means each step builds directly on the result of the one before. It lets us systematically dismantle the polynomial and find its exact roots without ever having to guess. Alright, this right here is the engine that drives the whole theorem. And I know, it lets us systematically dismantle the polynomial and find its exact roots without ever having to guess. Alright, this right here is the engine that drives the whole theorem. And I know, it looks pretty intimidating. But its job is actually pretty simple. It's designed to break down our massive polynomial and then build the solution, one piece at a time. Let's take a look at how the different parts work together. Okay, enough talk, let's see this thing in action. We are going to put this formula to work on our 18th degree monster and just watch the magic happen step by step. That big formula is really made of just three key parts. First, you've got binomial coefficients, which help adjust and weigh each term. Second, there's a piece that uses the original numbers from our polynomial. And third, the really important one, is the recursive term. That's where it feeds the last answer back into the equation to find the next one. So our mission is pretty clear. We're going to use that formula to calculate 18 special values, these symbolic coefficients. Think of them as the key building blocks we need to construct our final answer. Okay, here we go. We start the process. The first coefficient we calculate turns out to be 0. All right, on to the next one. The second coefficient is also 0. Okay, interesting. In fact, as we keep running through the calculations, we start to see this amazing pattern. Every single result is 0. And this is actually fantastic news, because all these zeros are going to make our problem way, way simpler. And then, bam, at the ninth step, the pattern breaks. We finally get our first non-zero number. Now, it's a massive number, sure, but it is an exact one. This is the first building block that really, truly matters. So after that one exciting moment, you won't believe it, but the pattern of zeros comes right back for all the next calculations. Until we hit the final 18th step. And there it is, our second and last non-zero number. So think about that. After all that work, out of 18 building blocks, it turns out we only needed 2 of them. So, what was the point of all that? We've calculated our 18 coefficients, and now it's time for the big payoff. This is where we see all that hard work turn this incredibly complex problem into something surprisingly simple. Let's just take one last look at where we started. Remember this sprawling, intimidating equation? 19 different terms? It just looked completely unmanageable. But the thing is imagine, because almost all of our coefficients were zero, that entire horrifying equation just collapses into this. It's not an approximation. It's not an estimate. It is the precise, perfect answer. The very thing that classical algebra said is impossible to find. So why does this matter beyond just one wild math problem? Well, first, it's about precision. Things like cryptography or quantum physics, close enough is just not good enough. Second, it gives us a systematic, repeatable process for tackling other tough issues. And maybe most important of all, it pushes the boundaries of what we even think is possible in math. It really leaves you with a fascinating thought, doesn't it? If a problem that was considered unsolvable for hundreds of years can be cracked just by looking at it in a new way, what else is happening? What other great challenges in science and engineering, even in medicine, are just sitting there waiting for one new idea to come along and solve them?